My name is Caleb Harris, and this is my report for Lab 5 of Physics 2211. The Lab 5 physics assignment was to create your own experiment, and for this one I chose to examine the falling slinky. The purpose of the falling slinky lab was to examine the motion of a falling slinky and compare it to the computational model of the motion using glow sticks. The main physics principles are Newton's second law of motion, the position update formula, and the impulse equation. The momentum equation, momentum equals mass times change of velocity, and the impulse equation, mass times change of velocity equals F net times delta t, tie directly to the kinematic equation, and Vf is equal to v naught plus acceleration times time. Vf is the final velocity in meters per second, while v naught is initial velocity, also in meters per second. A represents acceleration in meters per second squared, and d represents time in seconds. The position update formula is final position is equal to initial position plus v average times delta t, and is used when net force is not constant, like in spring or orbit problems. Also, drag force and tension force played a role. Drag force was important because the bottom of the slinky moves, and tension is important while the bottom of the slinky is stationary. Finally, Newton's second law of motion also plays a role, which is represented by the equation F is equal to mass times acceleration. F is force in newtons and m is mass in kilograms. The main result of the lab was that the computational model was similar to the experimental data and that it accurately depicted the motion of the slinky. Both the experimental data and the computational model showed the position of the slinky to visually decrease. The system is the slinky, and the surroundings are everything else in the universe. The mass starts from a position of 0 meters in the x dimension, 0.002634848 meters in the y dimension, and 0 meters in the z dimension. The mass starts with a velocity of 0 meters per second in the x dimension, 0 meters per second in the y dimension, and 0 meters per second in the z dimension. I started the coding by editing the initial position and the mass. Also, the proportionality constant of the drag force was found to be 2.6. This is used later in the second while loop. Then, using Newton's second law of motion, the position update equation, and the momentum impulse equation, I edited the first while loop to calculate the position change while center of mass of the slinky was not moving. The net force was calculated by summing the gravitational force and tension force, and the position update equation, Newton's second law of motion, and the momentum impulse equation, they all allow me to calculate the velocity and position of the slinky while it's accelerated downwards. But for this part of the experiment, the slinky was still stationary. The next while loop was very similar to the first, except that the second loop accounts for when the center of mass of the slinky is in motion. Again, I used the momentum impulse equation, Newton's second law of motion, and position update equation to calculate the motion. Since the bottom of the slinky is in motion, I had to account for the drag force. I applied the proportionality constant of 2.6. The main similarity between the model and the data was that both slinkies were initially at rest, and then as the time increased, the position decreased. There were small discrepancies in the data graph that could have been caused by the outside forces such as the tension force from the slinky on the slinky. The possible sources of error are that the man's hand might have enacted a force on the slinky as he dropped it, and that I might have misplaced the center of mass while I was using tracker. Displacing the center of mass would drastically impact how tracker recorded the motion. In conclusion, the computational model was very similar to the experimental model. This lab involved the momentum principle, Newton's second law of motion, and position update formula. The main takeaway is that the model closely predicted the motion of the slinky. The small discrepancies could be caused by leaving out an outside force, such as the tension from the top of the slinky acting on the bottom of the slinky.